The PPT is not shared.
Not shared. Okay, okay. Sorry. Then you could have told me. Okay. How to new share? Huh? Your screen sharing. Is it okay, madam? Is it sharing now?
No,
No,
sir.
sir.
No, sir. Okay, okay. Then you could have told me I have covered 2-3 slides. 1 minute. This slide, then to one share. Now, madam.
Oh, yes,
Okay,
sir.
sir.
Oh, sorry. I think 2 slides are covered. Sorry. Okay. Okay. So these are the topics that I'm going to cover in this section. I already discussed. To begin with, frequency reuse concept very briefly in 1 or 2 sentences. What are the resources that are available at the base station and at the mobile user for making a call to and fro, that are known as the multiple access techniques, and the basic generic architecture of the communication system. I will cover it within 1 to 6 slides. And the rapid development of wireless communication today, and what are the significant features of the wireless communication, 1 slide, and issues of the current cellular systems, are the limitations, rather than issues, it is a limitations of the current cellular system, starting from 1 to 4G system in 1 slide. And this is the important one. In the evolution of the cellular systems from 1G to 5G, the evolution procedure means what are the how it took place with 3 and 5G, 3 slides, and what are the various complexities involved in this 4G communications, and that includes the WFDM. 1 or 2 slides. Maximum slides I have got, it is only I think 20 slides. To begin with, let me start. So this is my base station. This is the typical scenario in a particular cell. Base station I usually call it as a BS, and mobile phone or mobile station I call it as, I denote it with MS. And the communication takes place from mobile phone to the base station in a particular link that is called uplink. Okay, uplink. And base station to mobile phone communication takes place in the downlink actually. Okay, this is the take place. To enable, this is the scenario in a particular cell actually. To enable communication, some resources need to be allocated to base station. So in order to establish a communication between base station to mobile station or mobile station to uplink. Okay, but let me consider the how to establish a connection between base station to downlink. Okay, so there must be some resources to be allocated to the base stations. Okay, what are the resources? Resources means we have certain resources that are available for making a communication between any 2 objects. Is it visible, madam? Everything? Is it audible and visible, please?
Yes,
Yes,
sir.
sir.
Yes, sir.
So we began with a particular cell configuration. Cell base station is there. We are taking 1 mobile station. How to establish a communication between base station and mobile station we are discussing. So there must be some resources that are to be available at the base station, and those resources are, you can see here, frequency bands. Frequency bands resources can be frequency bands means some frequency must be allocated, and time slots, some time slots. Okay, and code, some set of codes, you can say, some set of codes. Okay, this is 1, 2, 3, and 4th one is the or any combination of the above 3. Of above 3. Okay, So this is usually what we call it as a FDMA, and frequency resourcing, sharing of the resource of frequency for making a communication between base station to several users. Similarly, time slots. If I have a time like this, I will divide this time into different slots to communicate with each mobile user. Okay, this is time. This is what is called time division multiple access. Set of codes. Instead of using this frequency division and time slots, I use a code division multiple access. Okay, I use both are orthogonal to each other, time and frequency. Let me discuss later. And any combination of the three, I can use frequency TDMA plus FDMA or TDMA plus CDMA or FDMA plus CDMA. Okay, there are three combinations. Okay, and FDMA, CDMA, TDMA, CDMA like this. Any combination of the three also. Usually we use the combination of these, any one of these three things. Okay. So let me discuss about this same thing. Let me mention about the frequency review also here itself. Generally, there are two terms here. Channel capacity. Channel capacity means it is not because let me define one or two terms here. That is so that it will be easy to follow the next slides. So channel capacity. Channel capacity means how much information we can send through the given channel. Okay, how much information we can send through given channel. Okay, this is what channel information says, and generally here itself, let me mention the frequency reviews also. Briefly, let me mention frequency reuse also, because it will be easy to follow. Next slides. Frequency reuse. So generally, a cellular system which has hexagonal cells covering a whole area without overlapping. Okay, generally we use a cell instead of a circle. We use this hexagonal shell like this. Okay, not square, not circle, hexagonal shell. So this hexagonal cells covers a whole area without overlapping in any geographic area. That is the reason for covering the using the hexagonal shell. Because if you use the circles, there will be see here. There will be gaps here. There will be gaps in between the circles. Whereas hexagonal shell means there won't be any gap here, like this. It's a closed overlapping of the cells actually. Okay. There is a purpose also. One more purpose is there. Why do we use hexagonal shells? That we'll discuss later. So here, the frequency reuse is one of the key concepts in the cellular system. What we do, the coverage of the cellular radio system is divided into hexagonal cells. So total geographic area will be divided into hexagonal cells like this. Okay, there are three cells here. 1, 2, 3. And the coverage of the cellular system is divided into hexagonal cells, which are assigned different frequencies. So this cell assigns a particular frequency 1, set of frequencies 2, set of frequencies 3. So each cell does not have adjacent neighboring cells with the same frequency as shown here. This is F1, F2, F3. So I never use F1 frequency set here. Similarly, I never use either F1 or F2 frequency set here. Okay, all three are distinctive. So this co-channel, so that there won't be any co-channel interference. If it are some co-channel, there may be some co-channel interference due to the high power of the base stations. We can reduce it. And cell capacity, because of what is the advantage of frequency reuse is cell capacity increases. Cell capacity increases. capacity increases, and the coverage area also extended. Coverage area also can be extended. Can be extended. Okay. The smaller the cell, the more the capacity. Remember that there is a relation for that. Okay. The main aspect of the frequency reuse is, so total frequency to cover a particular geographic area, total frequency is divided into number of that usage of the, you take any, you have a spectrum like this. Okay. What we do, the total spectrum is divided into number of parts. Let us say F1 set, F2 set, F3 sets, F4 sets. Okay. So the coverage of the cellular system is divided into hexagonal cells. Okay, and which are assigned different frequencies. Okay, F1 frequency I give it to this one. So F2 frequency I give it to here. F3 frequency I give it to here, like this. Okay, so that there will not be any adjacent channel interference. I never use two adjacent channels, hexagonal cells frequencies be the same. Okay. So let me, because this is only just two terms I have defined here. Okay. Okay, then now whatever that I have discussed in the previous slides, same thing here. What I said, to improve the coverage and coverage area and channel capacity, we use the frequency reuse concept. Okay. That is what. Okay. Here in more details, frequency to establish a communication between a base station and a mobile station, we should have some resources, and the resources can be a frequency, time, or code, or any combination of the three values. So the same thing I'm discussing in this slide. So base stations in turn may assign, when once some resources are available to the base station, it may in turn assign a portion of them to individual calls. Okay. So this is to support communication on both uplink and downlink channels. Okay. So there must be some frequency, time, and code division multiplexing resources must be available to this one. So whenever base station wants to mobile communication, mobile device, it uses one of these 3 or 4 combinations of the resources. Okay. Then only it can establish a communication. This is something like that. If you want to send some data from this point to this point, so it must be moderated by data. It must moderate some. You should use some particular carrier frequency which is moderated by this data. Then only it can go far distances. Okay, different modulations may be there. Here, different resources for establishing a call here. Establishing a call between multiple users. Okay. So amount of resources allocated to users depend on the current resource availability and the particular requirements of each requesting user. And you can see as the base station must be able to assign individual portions of its resources to support multiple communications. So multiple communication techniques like FDMA, TDMA, CDMA are required together with multiple access protocols also. We need to follow the protocols also, which gives access to these resources. Okay. So this means we need to use these resources along with their protocols. Protocol means what we'll discuss later. Okay. So this is the typical scenario. There are 3 cells here. Center of the cell is equipped with a base station. This is a mobile phone here. And when this user is moving from crossing one cell to the other class, this is what is called, without any call interruption, you can make a move from this cell to this cell. This is what is called handover. When he comes to this edge of this cell, this base station will hand over his responsibility to this base station. Okay, without interrupting the ongoing call. This is what is called a handover or handoff. Okay. And I'm not discussing this max techniques. This is the frequency, because everybody is familiar with this frequency division multiplexing. Total band is divided into number of frequencies. This is what FDMA. This is every user has its own frequency channel while sending. Okay. There are 4 channels, 1, 2, 3. like this. So this is the TDMA. So users share the same bandwidth here, but the transmit one after the other. These are the various time slots. 1, 2, 3. Okay. They use the same frequency. Okay. So here this is the code frequency. User signals overlap in frequency and time, but orthogonality of the waveforms is used to separate user codes. This is what is known as the CDMA technique. Okay. Or a combination of the three also we can use. Actually, the coverage of the large geographic area with a limited amount of spectrum leads to the reuse of the frequency actually in multiple locations. Okay, I repeat again. Covering the large geographic area with limited amount of spectrum leads to the reuse of the frequency in multiple locations. This is to avoid the co-channel interference. Okay, interference from the different users. Okay, and limited spectrum. Or I can say frequency reuse is the ability to reuse the same frequency. Okay, same thing I have here. I have given you. Here, more elaborately, the cellular mobile communications is designed to provide communication to moving users. This is the main objective of the wireless communication, from pedestrians to travelers in the high-speed trains. So every mobile system were not cellular. Early mobile systems were not cellular. Coverage over large areas was provided by a high power transmitter mounted on a tall tower. There is low capacity. In the very beginning slide, I mentioned that cellular communication provides large capacity. The coverage is large geographic area also said. So this is how actually. If I place a big tower here and covering large area and it responds to low capacity, I have a slide, one more slide I will tell. So the capacity is increased by enabling frequencies used in one cell to be reused under certain conditions. So each of these base stations covers a particular area of the landscape called a cell. So to enable base stations cover the landscape in such a way that the user can travel around and carry on a phone call without interruption. This is what handover. So the procedure of changing base station at cell boundaries is called the handover. Okay, you can see here a group of cells here. Group of cells here you can see. This is one group of cell is called cluster. Cells called cluster. This is the cluster boundary. This is 1, 2, 3, 4, 5, 6, 7. Okay. So the frequency that is used in these cells, the set of frequencies that are used here, will be used here only, not anywhere else. You can see here. So that there will not be any co-channel interference. The frequency that is used within the cell also, within the cluster also, this is different and this is different. Okay, the same frequency is reused in another cluster with the optimal distance. This is another cluster. This is the second cluster. This is cluster 1, cluster 2, cluster 3. Cluster size and the radius of the cluster, everything will depend upon some design issues. Okay. And if you see here, as I mentioned, early mobile systems of the cellular system, mobile systems of the cellular communication were not cellular actually. So their coverage was very they cover over large area, but they provide low capacity. The reason is they are not cellular. Because the coverage over the large area is being provided by a high power transmitter, which is mounted in a tall tower, resulted in low capacity. And the thirds, this is you can see here. If I try to cover a large area with a high power transmitter, you can see here. So there will be an adjustment. There is a interference area between the two areas like this. adjacent channel interference as well as inter-carrier interference also here. Okay. Conventional radio telephone, this is what we were using early days. So this cell radius is around 30 to 50 kilometers area. Okay. They were not using this frequency resources like FDMA, TDMA techniques also. So now coming to this hexagonal cell structure. You see, you can hear the same thing I have already discussed. So the set of different frequencies used in group of cells. So in this particular group, particular cluster, group of cells is nothing but a cluster. Group of cells means cluster. So different frequencies used. I use one frequency here, F1, F2, F3, F4, F5, F6, F7. I have a limited spectrum which is divided into some, let us say, 7 groups. The same 7 groups, we use of the same frequency set in a other configuration. Here I am using same set. This is F2. I am using F2 here. I am using F2 here, F2 here, F2 here, F2 here. And sorry, F2, this is F7, F7 like this. We use of the same set of frequencies over a large geographic area in a particular designated cells configuration. So the cluster is repeated by linear shift. Generally, how do we? These are the design considerations. Steps along one I direction and steps in the other direction. J direction is will go by taking a 60 degrees linear shift, actually anti-clockwise direction. These are the design aspects. Actually, I'm not covering these aspects. Actually. Okay, cell radius. So these are the number of cells in a cluster. How many clusters can be accommodated in a particular geographic area? So these are the design aspects. What you can see here, the frequency we use drastically increases user capacity and spectrum efficiency. You can see here some formulas are there. How do they improve the capacity and the spectrum efficiency? And here, this is what actually to reuse the particular frequency in a cluster in a cluster stuff like this, just to make a move steps along the in one direction. Suppose let us say, so this is one cluster. One cell is not written here. One cell is not there. Okay, so okay, move in one in I direction, and then steps in the J direction like this. Okay, so here also like this. J direction. Which has a let us say it has got some S number of duplex channels. Let us say a cellular system has got, so let us say ATEL operator or BSNL telephone operator has been given some S number of duplex channels, means uplink plus downlink purpose. So each cell is allocated a group of K channels. Okay, each cell means this cell, this particular cell is divided among each cell is allocated a group of K channels. Okay, so always my K must be less than the total number of channels that are given to a particular operator. Okay, so then the S channels are divided into N cells, these S channels. Okay, so the total number of available radio channels equals to K times, K means how many frequencies that are used in a cell times the number of cells. Okay, channels per cell times number of cells, number of cells, sorry. Okay, channels are let us say 7, number of cells are let us say 7 suppose, then 49 total number of available radio channels here. Okay, originally I have only 7 channels, then it is increased to 49 channels. Okay, the same thing I am continuing here. So I have n cells. I have n cells. Total number is S number of channels. Total channels. Okay. Total channels. I have K channels. I am using K channels per cell. Number of cells are number of cells are n actually. So K10 is the total number of channels. So now you see the n cells, n cells, which use the complete set of channels is called a cluster. This is a cluster because this n number of channels 1, 2, 3, 4, 5, 6, 7. There are 7 cells, which is nothing but your n. Each cell is using k channels of frequency sets. So k into n is the total number of frequency channels that are available to cover this particular geographic area. Same thing is getting repeated everywhere in the geographic areas. Okay. So now you can see the cluster can repeat m times with the system. So how many times I can repeat this cluster? This is one cluster. I repeat, there are s number of total channels. Okay. Each cell uses some k number of frequency channels. Number of channels are n. Then k into n is the equals to my s. Total I am dividing like this. Okay. So same thing is getting repeated everywhere. So m, how many times I can repeat is m times I can repeat. That means m into k into n is my s. Total number. So this is the means the coverage capacity. The capacity how it is getting multiplied. You can see. Originally I have only k into n only, but it is multiplied by m actually. This many times my coverage capacity is channel capacity is increased. You can see. Okay, this is what m k n are because kn is nothing but your s. So the capacity directly proposed to the number of replications. How many this kind of clusters I can use? Okay, you can see here with this slide. What I'm discussing is how the coverage capacity or channel capacity. You can say channel capacity is increased in cellular system. Okay, in a cellular system, how the channel capacity increased we have seen. Usually the cluster size can be 4, 7, 12. It depends upon my design aspect. I square plus ij plus j square, where n is the small this one. So this is not required for us. So with this example, what we have seen is how the channel capacity can be improved, increased. Okay. This is reuse distance. This I'm not going to cover, not required. This formula only. What is the reuse distance here between two clusters? Okay, between two cells. This is one cluster. This is another cluster. What is the reuse distance? Depending upon the cell size, it depends also. Okay, that is radius of the cell. Radius of the cell means from this point to this point. It depends upon the I and j movements also. Cell radius, reuse distance. And this is the radius of the cluster here. I can determine. So these are the design aspects of the cellular system. When I try to implement a particular cellular coverage area for the given frequency spectrum. Okay, these are some design aspects. What should be the distance between two clusters, centers of the clusters? You can say. Okay, these are some design aspects, and you can see here. A cellular system consists of 3 basic elements that we have seen here. Okay. Same thing is getting repeated here, but more information. A cellular system which consists of 3 basic elements that we have seen here. Mobile station, this is M, S. This is B, S, B, S. This is mobile station. This is this. Okay, each cell is equipped with a base station at its center. There may be a number of users here. Each base station is connected to its I want to make a communication between mobile station A to mobile station B. How can I establish a connection here? Suppose a mobile station A established a connection with mobile station B. So the end-to-end connection from this point to this point, it's not a direct contact. Okay. So how do I make a contact here is I make a communication, or I make a call from mobile station A to base station. This base station A. Okay. This is how actually from here to here, from here to here, and from here to base station, and base station to here. Okay, that is from mobile A to base station A, and from base station A to mobile B via some fixed communication links. Actually, these are the from base station to here, mobile station, and mobile station to base station. There may be a fixed communication links like this. Okay. So now coming to design of a mobile communication system is particularly challenging because of the adverse propagation effects actually. Okay, adverse propagation effect that we have studied already, but let's just mention here. This is the main problem with mobile communication is the adverse propagation conditions. Otherwise, there won't be any problem at all. So, which is experienced on the radio channel. Okay, radio channel means it may be due to the transmitting antenna, starting from antenna properties. Channel means all obstacles, and there may be problem with antenna of receiver also. Okay, 3 components again involved here. Okay, so the main propagation effects are usually distinguished, and they are path loss, slow fading, or shadow fading. Okay, or fast fading. Okay, fast fading. I can categorize the main propagation effects into 3 categories, 3 types. One is the path loss, slow fading, fast fading. Path loss usually suppose if this is a satellite communication. This is on the surface of that, some person is there. If there is no obstacle, this is a direct line of sight communication. Okay, even then I will have a path loss. Path loss means provides attenuation of the signal, which is proportional to the 1 by r square, distance square. Okay, and because of the shadowing, this is line of sight. Even though there is a line of sight propagation, there will be an attenuation in the signal. There may not be any phase change of the signal, but attenuation will be there. Okay, and this is line of sight communication. Okay, this may be due to the reflection. This may be due to a diffraction or scattering here. Okay, these are the things we'll see. We have seen multipath effects. So in the previous session, delay spread and the Doppler effect. At peripheral view only we have seen here. Okay, we have seen there at peripheral, and the slow fading, shadowing, and all we have not seen. These are the few details about the path loss. Path loss. It describes the average signal attenuation as a function of distance. Okay, it's a function of distance actually. That is, we can say here it is a as I said mentioned, it is proportional to the 1 by d square. Okay, it's proportional to the 1 by distance square root of the distance, square of the distance. Okay, and shadowing means So see, this is when there is an obstacle between, let us say this is a tree. So it absorbs some energy and something like a focusing of the light focuses, there is an object here, still you will get light here, attenuated light here. Okay, so that is what shadowing actually here. Okay, and fades occur, and this is what deep fades and all we have seen there, and fades occur roughly once every half wavelength actually. Okay, deep fades, sometimes deep fades occurs for every half wavelength distance, half wavelength of the signal time periods. Okay, very it varies, fades varies from for very small distances. How it will happen we'll see. Okay, because we have seen there multipath fading can result in a relatively fast signal fluctuations. Earlier we have seen, so exactly how fast depends on the speed of the mobile, that is a Doppler effect. Our base station means transmitting station, or the dynamics of the surrounding environment also. Okay, so this is what very briefly I have discussed about the communication system challenge problems associated. Now we can see here what are the main reasons that are for the rapid growth or development of the wireless mobile communication. You see here. Okay, these are very important reasons. So this is mainly due to the international liberalization of the telecommunication services, opening and deregulation of the world markets, improved modulation and coding techniques. Okay, this includes OFDM is the past. Okay, new modulation techniques have been developed, new coding techniques have been developed to reduce the BER, space-time codings. Okay, and extension of frequency range around and beyond. Of course, this is now beyond 10 gigahertz to 100 gigahertz. Now we are going. In future, we may go up to 300 gigahertz. This is the unlicensed spectrum. Okay, and propagation progress in the semiconductor technology also. VLSI circuits based FPGA boards, CMOS technology, and gallium arsenide compound semiconductor material technology also. We have seen, we have studied the gun diode and all there in microengineering. Okay, how effective it is for generating the micro frequencies. Okay, which exhibits negative resistance characteristic because of the RWH two values in their conduction band. Okay, so the same gallium arsenide technology is used, based indium phosphide and cadmium materials that are used in the semiconductor technology also for their various characteristics. So one more, the most important thing for the rapid growth or development of the wireless communication system is that we are able to model the propagation characteristics. This is the thing, main development that took place. Okay, we are able to model the channel to some extent. So this is the channel, receiver, transmitter. So earlier we were not having the channel modelings. Channel models were not available. Means precise, accurate channel models were not that were available earlier, including rally fading channels like that. So to cater the needs of the extremely complex environments, we have the channel models like this. Okay, developments, I mean research, because of the research there are very good developments in case of the channel modeling, etc. That is what. Okay, so these are the reasons for development of the wireless communication channels. Okay, and what are the problems that are associated with the current cellular systems? You can see here. From 1982 to the present, And or you can say the development of wireless communication has gone through 4 generations. You can say 3, comma. So the slide was prepared long back. 4G and 4G. Okay. So development of wireless communications has gone through 4 generations. Okay. The 1G was based on the analog speed that let me discuss later on. So nowadays LTE, long-term evolution and its extension. Basically nowadays we use the LTEA, which is nothing but the 4G. There was no 4G actually. Okay. So what is called LTE advanced is nothing but the 4G. Let me discuss the 4G technology has been developed because of the 3 main features: MIMO technology, OFDM, and the cooperative communications. Okay. And what is the need for the development of the 5G technology? These are the reasons. Okay. Why the whole world is looking for the new green communication technology, that is 5G. These are the basic reasons. Okay. You can see here there is a urgent need to develop mobile communication technology, what is called the green revolution technology. Okay. So what is happening is with the development of industry and worldwide deployment of mobile network, dramatic increase in number of wireless system users. There is a very tremendous increase in the number of users. So powerful smartphones that what we are using now, laptops are becoming popular day by day. So driving video streaming and other bandwidth hungry applications like teleconferences and 3D holography, etc., are increasing day by day. So because of this, what is happening? Carbon dioxide emissions are increasing and sea levels are rising and global weather and air pollution are becoming more and more severe. Okay. The reason is almost 25% of the power consumption is 25% of the power consumption mainly due to the mobile phones only. Mobile phones that include smartphones and laptops, or you can say IoT devices. So report, if you see the report of 2012, it shows that telecommunication infrastructure and it amounts to 25%. You can see here, and it is growing annually power consumption. And also IP data handle is expected to increase by over a factor of 100 to 500 exabytes by 2020. Okay. So at present, the present cellular communication systems are not able to meet the requirements of these things. So they are not able to meet this requirement actually. Okay. So that is why we have to go for and spectrum issues also there. So there is a need to go for a new communication system. So in comparison to 4G, if you see new communication system, it should achieve 1000 times capacity. A new communication system like 4G, it should give us a minimum of 1000 times capacity, 10 times more capacity than the 4G. Then only we can use all these things. Okay. And one more thing is, this is one requirement, 10% more spectral efficiency mode should be there. 10 times more spectral efficiency. That is the important one. And it needs to this energy efficiency, which energy efficiency means to reduce this one. Energy efficiency. Okay. And data rates, more data rates, higher data rates, and 25 times the average cell throughput. 25 times average cell throughput should be increased. Okay. So revolutionary wireless communication technologies that are capable of catching the mobile traffic growth while reducing the carbon dioxide emissions are compelling actually. Okay. So this is the reason why we should go for a 5G technology. I repeat again, we should have a wireless communication technology which can give me 1000 times more capacity than the 4G and 10 times more spectral efficiency and higher data rates of the order of 10 Gbps, something like that, and 25 times the energy cell throughput. Throughput is the actual bandwidth. So the revolutionary wireless communication technologies that are capable of catching the mobile traffic growth while reducing carbon dioxide emissions and it reduces the sea level rise. Okay, it is compelling us to go for a new technology. Okay. So let me go through 1G to 5G quickly. I will spend more time on the 5G, but evolution just let us see. So I think most of you have never used any 1G. I believe I have not used. In India, it was not there. Okay, even till today, some Americans are using the 1G telephone. So 1980s brought the 1G telephone network, mobile phone network. It was with only voice, and it's an analog based service. And if you see the top speed of the transmission of 1G network is around 2.4 gigahertz. It's only 2.4 gigahertz. Okay, 2. I have not given. I think I have given it. 2.4 kbps. Okay, and it was using the frequency range of two bands. It was using. Europeans were using 900 megahertz frequency band, and Americans are using 800 megahertz band. This was the main features of the. It's a voice only, and it's analog. Okay, and this technology was mainly based on the frequency modulation and FDMA schemes actually. Okay, and the top data rate transmission reach actually top speed of the data transmission is 22.4 kilobits per second. Very low. Cannot establish any connection here. Okay, and if you see the 2G mobile communication, it was introduced in the this 2G network began in 90 or 91, and it allows the cell phones to move into the digital world. And the 2G allowed for call and text encryption as well as SMS also. And picture image, most of you must have used the MMS service. Picture messaging and MMS was also there. The maximum speed in 2G was around 50 kbps here. And it operates in the same band. It operates in the same 800 by 900 megahertz. Of course, 2.5G onwards, they have shifted to the 1800 megahertz to 1900 megahertz frequency band also. There were mainly two standards in the world, GSM and CDMA1. GSM was the technology which uses the TDMA and FDMA by the European people, and the CDMA was the technology being developed by the Qualcomm in USA. Okay, they use CDMA code for utilization of the frequency, utilization of the resources to establish a call between the base station and the mobile phone. And to begin with, 3G, quickly review the 3G features. Okay, the advent of 3G networks with more data, video calling, mobile internet began in 1998. Okay, and 3G networks reach 2 Mbps on stationary or non-moving devices and 384 kbps on devices in moving vehicles. So most of you must have used the 3G on a daily basis. Okay, so now coming to the 4G, if you see 4G, I compare the 4G features with the 5G in next slides. 4G, it was developed. Actually, it was developed as the starting point for 4G was the not as 4G. It was the LTE. It was the LTE, long-term evolution. Okay, now LTE A, something like that. LTE AB, something like that. Okay. The 4G is the current standard of the cellular networks. It was released in the year late actually. It was in the it was released in the year late 2000, first decade of the 2000 year, and it is 400 times faster than the 5G. I think I have given here 1500 times faster than the 3G. And the principal technologies that were used in 4G are MIMO, adaptive modulation, coding, OFDMA, and fixed and cooperative relaying networks. Okay. Let me take water. Now coming to let me compare the 4G versus the 5G. Okay, 4G versus 5G. One of the biggest differences between the 4G and 5G will be peak capacity and latency. Okay, or you can say the main difference for the user lies in what is called latency. Capacity anyway it is increased, but the problem with the 4G was not with the capacity. The main advantage of the 5G is the latency. You can see here, latency. You may ask a question, why? What is this latency? It has got a lot of importance. Okay, 5-10 minutes later. Latency. Another big difference is the bandwidth size, but let me elaborate more on this latency. This is very important thing actually. Okay, so this is the delay that the network imposes for a packet of data to travel across the network. Okay, it is not what we usually call the speed that we measure in megabits per second or gigabits per second. It is not the speed. It is the data to traveling time actually across the network. Okay. For instance, we need a high speed in the order of megabits Mbps to be able to see a streaming high definition video. To watch a high definition HD TV, we need at least minimum of Mbps speed. But to be able to remote control a car or a plane or a drone, what we need is very low latency. I will explain you how actually. Without latency, low latency, you cannot achieve anything. For instance, we can say in the network in the order of to be particularly in the near real time or real time, what is captured by onboard cameras and send the controlling commands from the remote control to nearby remote controller in near real time is the most and highest need in the present day. I repeat again, latency is the travel time of the packet across the network. It is not the speed, remember. Okay. Similarly, to control the robo or a drone or a aircraft or something like that, okay, car, okay, you should have a very low latency in the network. Latency of the order of 10 milliseconds. Okay, usually we may achieve 2 milliseconds in 5G. Okay, without low latency, you cannot watch a high definition TV. Okay, video streaming is not possible, and you cannot remotely control drones, etc. It's like low latency. Low latency is a feature of near real time operation. Okay, so coming to the 5G. The 5G stands for the fifth generation, and we know that it is a successor of the 4G LTE advanced system. It provides applications to near real-time functionality, okay, which was not practical or possible with the 4G system. Actually, there was no 4G actually. Since there was an enormous gap between the old 3G standard and the new 4G. So companies, what they thought, they wanted to make sure that customer space knew they were receiving better service than just the same old 3G. So they came up with a work, they came up with a new idea, and this idea was the LTE. Actually, there was no 4G. Even till today, LTE advanced only. Okay, that was the long-term evolution. The original idea was that it represented as a long-term evolution toward the 4G standard. But the clever marketers figured out was that they could present in something like a greater than the uh, uh, standard if they simply added 4G before it. Okay, that is why they call it as a 4G LTE. There was no 4G actually. It's only LTE. Some companies, uh, cellular mobile phone operators, they're simply adding the 4G, but it's a 4G LTE. And this is what about the latency. Latency, as I said, without latency, near real-time applications making use of this mobile communication is not possible. One more thing you can see here, it measures the time it takes for the data to go from source to the destination in milliseconds. Okay, just to give some context, it takes at least 10 milliseconds for an image seen by the human eye to be processed by the brain. Okay, at least to store, to memorize the particular memory image in our brain, at least we should be able to see the image a minimum of 10 milliseconds time. Okay, otherwise we cannot remember the image. Brain cannot distinguish anything. So low latency is vital for real-time reactions in missions or cars, and it could also be make cloud gaming possible also. Okay. So we are achieving less than 2 milliseconds low latency with the 5G systems. And you can see here the differences between the 4G and 5G. Here, the differences we can see here. This is the 4G, this is the 5G features. Okay. As I said, the 4G uses the spectrum bands below 3 gigahertz. Okay. And 4G uses the spectrum bands of below 3 gigahertz. 3 gigahertz. Okay. It uses a maximum frequency band of bandwidth. It uses only 20 megahertz WDM. Okay. In 4G, we use tower radiuses. Usually, it may range from 5 to 10 kilometers area. Okay, of course, it depends upon the population density and usage characteristic. And usually, this 4G delivers a speed of 10 Mbps. Speed, okay. And the peak speed, it may go up to maximum 100 Mbps. 100 Mbps. So this is the reason actually. Peak speed should reach 100 Mbps. Then only we call it as a 4G. That was the standard developed by the UMTS and the 3GPP. With the till now, our operators are not able to reach this figure. Then they were not allowed to use the 4G. But that is why they call it as a LTE advanced with the tag 4G. So the main difference of the user lies in what is called the latency that we are seeing. Okay. So these are some of the speeches of the 4G. If you come into this 5G, I'm beginning with the 5G. This is the latency, 1 millisecond. Okay, and speed may go up to 10 Gbps, and peak capacity may go 5G in ultra wideband sector, and 4G compared to 4G in Mbps. In it is in the order of less than gigabytes actually, or less than 1 gigabits. So 4G could support up to 1,000 times more devices than the 4G, leading to a world more connected than the ever. So this shift is critical as billions of IoT devices come online and strain existing 4G network. Okay. And we know that the existing wireless communications uses subbands of sub 6 gigahertz frequencies. So mainly due to the spectrum scarcity in lower frequency bands. That is the reason in 5G we go for millimeter waves here. millimeter waves. Starting from 3 gigahertz to, I may go up to 300. Presently, it was planned for, they have planned up to 100 gigahertz, 28, starting from 10 gigahertz, 28, 30, 60 around, and then 100, and below 100 somewhere like that. This was the present plan. Up to 4G, we were using only less than 6 gigahertz frequency. In fact, 2.1 to 2.6 gigahertz frequency only we were using. Okay. We call this frequency is known as the sub 6 gigahertz frequency. This is the main advantage. 5G, we can achieve 1 millisecond. This is the below 6 gigahertz in case of 4G and below generations of cellular communications. They are all called millimeter waves. Okay, but they, because they vary in their wavelength starting from 1 millimeter to 10 millimeters. The corresponding wavelength is 1 millimeter, 10 millimeter. Okay, that is why millimeter, sub millimeter, 1 millimeter. This is 1 millimeter, 10 millimeter. In case of 4G, you can say 10 centimeters of wavelength. So there is one major drawback to millimeter waves. You can see here, they cannot easily travel through buildings or obstacles, or they cannot be absorbed by the rain or foliage. That is why 5G networks will likely augment traditional cellular networks with another new technology called small cells. Okay, small cells are required in case of 5G because these millimeter waves cannot travel much distance. They may travel maximum of 6 to 7 meters because of high attenuation. And moreover, they cannot travel through walls. So in addition to broadcasting over millimeter waves, 5G base stations will also have many more antennas than the base stations of today's cellular networks. That is what is we call multi-input and multi-output. Many antennas, multiple inputs and multiple output. So we use 2 or more transmitting and receiving antennas to send or receive more data at once. Okay. So these are the other techniques. These are the techniques that we call millimeter waves, massive MIMO, small cells, beamforming, and full duplex, and latency. We achieve all this with all these things. We achieve the low latency. Okay. If time is there, we'll discuss more in each one objective. We can discuss in detail. Let me cover the whole thing first. So in this slide, you can see, unlike the wired communication, I'm just going how the 4G in the 4G system, what are the problems? Why do we go for wave beam? I'm just discussing now. So unlike wired communication, which uses the fixed path, signals in wireless communication can reach user using multipath. So all these components known as multipath components. So you can see here. So these are all the multipath components. This one. This is line of sight. NLOS. So once they come to the mobile station, they all get added up like this. Okay. So these are the delays of various all the 3 paths. For line of sight, it is only delta of t. So all the components known as multipath components, they may have different channel gains and different time delays. Okay. They will have different channel gains, different channel gains. And different delays. So this is a delay, this is a channel gain. Okay. So the combined effect caused, it would be known as the multipath fading. That is what we have seen. It is mainly due to the scatterers. Scatters means what we have seen earlier, scattering objects. Okay, mainly caused by the buildings, trees, and other objects. So next, coming to the how a particular delay, means path delay among these transmission paths. Okay, how the difference in the path delay is making a communication system quality, how the communication system quality is getting degraded because of the multiple paths delays. Particularly, we see in the waveform case. You can see here. This is what is called the delay spread. I am coming to here. We can see multipath fading. We have seen. Okay, these components known as the multipath. They may have a multipath components will have different channel gains and different time delays. That's what we have seen. Now coming to the delay spread, you can see here. Delay spread, as a consequence of the multipath propagation, the duration of the symbol gets extended. That is what I have discussed earlier. Okay, symbol duration is getting extended at the receiver than compared to the when it was transmitted at the transmitter side. Okay, so this may interfere with the next symbol. So this is called the ECE at crosstalk. You can see this is the first. Let us say this is one symbol. This is symbol 2. Transmitter is sending at the receiver side. Because of the delay, you can see here. Because of another path, it got delayed and it received at the receiver as this one. The center one. Okay. So because of this thing, what is happening? There is an interference between the second symbol and the path means delayed version of the first symbol. This is the delayed version of the first symbol. Let us say this is the first symbol, second symbol. This is the delayed version of the first symbol. You can see the interference here. This is what is called intersymbol interference. So to avoid this intersymbol interference, we may add gauge band here, something like this. We may provide some space between two symbols, sufficient space that corresponds to the maximum delay path. Suppose if there is a symbol that is arriving because of the multiple path, it should arrive in between actually. Okay. So frequency selective fading. These are the details of minute details for waveform symbols only. I'm just mentioning. Okay. So signals having higher bandwidth than the coherence bandwidth of the channel, and that kind of situation faces a different variation of the different frequencies. That kind of channel faces different variation at different frequencies. So this is called frequency selective fading. This distorts the signal in time domain. Okay, I repeat again. The signal bandwidth is more than the coherence bandwidth of the channel. Coherence bandwidth of the channel means, I write here, the signal bandwidth. S of t is the signal. So signal bandwidth is V1 and the channel coherence bandwidth. Channel coherence bandwidth is B2. If my B1 is greater than B2, then I will have frequency selective fading. Coherence bandwidth means the amount of coherence time means the amount of time that channel characteristics are not changing. Inverse of the coherence time is nothing but the coherence bandwidth. Okay. So to avoid this frequency selective fading, usually we go for equalizers. Complex channel equalizers we use, so that the carrier interference can be reduced. This is the to describe the frequency selective fading. You can see here, this is the bandwidth of the signal, and this is the coherence bandwidth of the channel. Coherence bandwidth of the channel is flat up to this portion only. From beyond that, it is getting, there are fades, amplitudes are getting reduced. You can see here, variable attenuation here. Okay, this is the signal bandwidth. The signal bandwidth is more than this one. The signal bandwidth is more than, this is the signal bandwidth. Okay, yes, this is the, from here to here, it is the channel bandwidth. Channel bandwidth. Okay, the signal bandwidth is here. The signal bandwidth is more than the coherence bandwidth. Then it's kind of this is the coherence. Sorry, this is the coherence bandwidth. The signal bandwidth is more than the the signal bandwidth is more than the coherence bandwidth. Then this kind of fades occurs. Frequency selective fade occurs. Okay. So generally, you can see here frequency selective fading. You can see usually. So generally, suppose we see just to explain it in another way, you can see, suppose this is an impulse pulse, one path which is receiving the which is reaching the receiver with an impulse response of h of t at time. Okay, and there is another path whose impulse response is like this with the same amplitude. This is T and this is capital T, you can say. This is capital T. There is a multiple path. There is another delay which is receiving, this is at Tm time T equals to this one. This is time. So single path impulse response is, you know that this is impulse, this is the impulse response. Okay. This is impulse response, amplitude. It's a flat. Okay, this is the impulse response to flat because it contains all the frequencies with equal amplitude. This is the flat fading because it may go up or down, but it's flat. The entire bandwidth spectrum, the fading remains same here. Okay, this is known as the flat fading. So all frequency components are getting affected equally here. Okay, equally here. But here, in case of here, this kind of symbols you see here, suppose the first symbol is like this. And the second symbol is like this. Suppose this is the first one. Second arrived the receiver with this delay T. Okay. So then what is happening? Sorry, this is one, not this one. The second one, suppose if it arrives with a delay of pi, suppose. Then what will happen? Their phases are almost 180 degrees opposite phase. They get added up and you get only 0 amplitude here. Okay. So this is h of u, h of omega, frequency response of the impulse channel. It is constant. So here the gain is constant here. In case of frequency flat fading, its gain is constant. Okay, it may go up and down. That's all, because of some multiple path effect. But there is a case where the one of the path may add to the original path with this phase shift. Then you will get a deep fading. You don't get anything here. Okay, you can see here for this kind of thing, you will get a frequency response. If you see the frequency response, it will be like this. This one. So this will be how I have drawn is. You can see here. This is the frequency transform of frequency transform of h of t, which is nothing but a flat horizontal curve. Okay, so that is what we are doing. I have not drawn the phase plot of the Fourier transform. Phase plot, if you see here, okay, it's a quite complex one. If you try it here, because of the as you know, this is nothing but the Fourier transform of the phase diagram of the first pulse is nothing but zero phase shift. Okay, this is omega, this is of omega. It is zero shift, it will be like this only. There is no phase shift here. Whereas for this signal, this is the line of sight signal, this is the NLOS signal. So it reached the receiver with a delay of x minus t. Okay, so the Fourier transform of t minus t minus x of t minus t, this is. So this signal corresponds to x of t, whose magnitude and phase plot like this. This signal corresponds to x of t minus t. I have given the frequency domain response here like this. Okay. X of t means if I try to transfer this x of t, what is its Fourier transform? If I transform into the frequency domain, if I take the Fourier transform, what would be the term? It is e to the power minus j omega t, capital T, times x of j omega. Okay. If I take the Fourier transform of x of t minus t, this is the e power minus j omega t. Means this term, if we see here, this is the frequency response of the original signal. Okay, this term is j omega t term. So that means it rotates in the anti-clockwise clockwise direction. Always e power j omega t term rotates the anti-clockwise. This term rotates in the anti-clockwise direction like this. So this is what is called this angle. It rotated with an angle of t. This is omega t. This is pi. This is minus pi. Okay. This is the slope actually. The slope in case of without delay, it's a flat actually. The slope rotates like this. Something like cos of omega t, without any phase shift, it goes like this only. It relies on the real axis like this only. So, but this is the delayed by t units. I mean, that means it may come this side. There must be a delay. There must be an instance. At some instance, it may come to this side. The slope may come to reach this one. That time, the delay corresponds to pi. This is the case. That corresponds to deep fade. Okay. Deep fade. So this is called, so this here, if you see here, what is this value here? This corresponds to this one. So this is minus pi by 2. Minus pi by 2, because my omega t equals to pi. Omega t equals to pi. So t equals to pi by t equals to omega. Okay. This is minus pi by 2. This is plus pi by 2. This is plus pi by 2. And this you can see somewhere here 2 pi by 2, 2 pi by 2 like this. So I just drawn the phase plot of the frequency transform. Phase plot of the frequency transform corresponds to same constant line like this. Okay, something like the cos 0. Okay, this is like that. This corresponds. But in case of delayed version, the phase plot corresponds like this. Fourier transform of the signal like this. That is x of t minus 1. Okay, like this. So that is why deep fades occurs actually. This kind of deep fades occurs means there is exactly two signals are getting added with opposite phases, corresponds to 180 degrees. Then you don't get anything, no signal input at the receiver. Okay, so some here, some here. So generally, way of doing what we do, we convert this frequency selective fading into flat fading. Flat fading. How do we select, So here, flat fading, suppose if it's a narrow band means, suppose here, it's a narrow band, there is no fading. It's, even it is here, narrow band, but it's if the signal bandwidth is like this, wide band, it encounters the frequency selective fading. Okay. What we do in OFDM, I'll tell you in the next slide. What I will show you. So in OFDM system, we convert this frequency selective fading purposefully into frequency flat fading, purposefully by increasing the symbol duration mode. Okay. In case of single frequency system, the symbol duration is very, very low. In case of waveform system, the symbol duration is very high and the frequency bandwidth is very, very low. Remember, both are inverting terms. Okay, you can see here. And one more thing is interchannel interference. You can see the interference like this because of the delay. Okay, so all these limitations, multipath fading, delay spread, frequency selective fading, intercarrier interference, combined with selectivity of bandwidth, gave rise to MAG techniques before driving it to OFDM. Okay, you can see here how I am able to get overcome this frequency selective fading in case of OFDM. You can see, I will explain now. Here, suppose you can see here. Suppose if the signal to be transmitted having a bandwidth of B. Okay, I have written. Suppose a signal to be transmitted having a bandwidth of B. Okay. Now what I'm discussing in this slide is how the waveform system is reducing the intersymbol interference and frequency selective fading. I'm just discussing here in a simple pulses diagram. Okay. Suppose, let us say, if the signal to be transmitted is having a bandwidth B and a carrier frequency FC. Okay. Then the symbol rate would be TS is equal to 1 by B. This is the symbol rate. Okay. So, okay. So for a single carrier wideband channel, okay. First point is, suppose signal to be transmitted is having a bandwidth B and FC as the carrier, then symbol time period is TS equals to 1 by B. And if you see the time period of the symbol, which is equal to 1 by F, TS equals to 1 by bandwidth, which is equal to 1 by microsecond. 1 by microsecond means the more the bandwidth. Okay. So if delay spread is of the channel is, let us say, 2 microseconds. The combined TS will be, suppose, let us say, if there is a delay spread of channel is 2 seconds. You can see here, it is visible or not, I don't know. This is the, let us say, this is the carrier with 1 microsecond period time and 1 megahertz bandwidth. Okay. There is a delay of spread of 2 microseconds. That means this symbol appears at the receiver after 2 microseconds time. Original time period of the symbol is 1 microsecond. If there is no delay, it would reach at the 1 microsecond time. This would be. But because of the delay spread, because of the multiple path, it receives after 2 microseconds. So that means there is a spread in the time symbol. So the total spread in the time symbol is equivalent to the 1 microsecond plus 2 microseconds, which corresponds to the 3 microseconds. That means what is happening? This, because of the delay spread, it occupies 66% of the combined TS. You can see here. Okay. This is the symbol to be transmitted whose time period is 1 microsecond. Okay. If if it reaches the receiver as it is, it would be only 1 microsecond only. Okay, there won't be any delay spread. Suppose because of the multiple path, one more path has come, the path arrived at the receiver after 2 microseconds. So original 1 microsecond plus 2 microseconds, it became 3 microseconds here. This is the spread of the symbol, time spread of the symbol here. Time duration is spread here like this. Okay, 2, 3 microseconds. Originally it was 1 microsecond. So that means what is happening? The efficiency is reduced by 2/3 of it is reduced. Na? So the efficiency reduced by 33%. Okay, so it is difficult to control this delay spread, but can be minimized using multiple subcarriers which are less than bandwidth. This is the technique that we use. We cannot avoid the delay spread because multiple objects will be there in the channel, but we can minimize this its effect by using a multiple subcarriers of lesser bandwidth. What I do here, you can see here. So earlier I have a whole frequency spectrum like this, whose bandwidth is 1 megahertz, and I was using only one carrier, one FC. So because of this, I will have this kind of problem, this delay spread problem. So what I do to get rid of this kind of problem, so it is better to have, instead of a single carrier 1 megahertz, we divide it into 100 subcarriers of 10 kilohertz. So 1 megahertz equals to 100 into 10 kilohertz. 10 kilohertz. So 100 subcarriers I divide. The whole spectrum will be divided into like this 100 times, whose width is 10 kilohertz like this. There will be space. The spacing between two subcarriers is 10 kilohertz like this. Okay, or I can say bandwidth of that particular subcarrier. So each, then as we know that bandwidth equals to 1 by symbol period. Okay, so earlier 1 megahertz bandwidth FC corresponds to symbol period is equals to 1 by 1 megahertz equals to 1 microsecond. Here now the bandwidth is, the total bandwidth is divided into 100 10 kilohertz. So this is 1 by 10 kilohertz, which is equivalent to 100 microseconds. Equivalent to 100 microseconds. Okay, that means what happened? Original bandwidth, the original time period of the signal was 1 microsecond, but I'm converted into 10 microseconds. Original before OFDM, symbol period was this much only, 1 microsecond. But after taking the OFDM modulation, I'm using the symbol periods of the symbol period duration as this much, 100 like this, 100 microseconds duration. Okay, so this is what I did. So total frequency band is divided into number of chunks like this. Total here 1 megahertz is divided into 110 kilohertz symbols, whose bandwidth is reduced. Bandwidth is reduced, but symbol period is increased. Okay, so this concept is used in FDMA, which uses slowly modulating subcarriers at a high symbol duration. And as you can see here, these subcarriers are modulated with data like this 100 kilohertz symbols, whose symbol period is 100 microseconds. Okay, so they will be modulated, each carrier is modulated with one data symbol, and the guard bands are used to separate them like this. The transmit signal is nothing but the summation of all the symbols. Summation of all the symbols means, you can see here, summation of all the signals. So originally, let us say this X1 is one symbol modulated with one carrier, that is FC1. F1 plus x2 into F2 like this. So totally I'm converting into real time in Fourier transform. It is x of n times e power j omega t. Okay, real part of this one actually I take. So transmit signal is like this. Transmit signal. This is not what this is actually n equals to what this is exactly represents. This is the IDFT, inverse discrete Fourier transform. Okay, this is the symbol period. This one actually. So here, this is what exactly what we are seeing here. So WAVE users are provided a set of subcarriers overlapping in frequency domain. They are overlapping. All the subcarriers are overlapping in frequency domain. You can see, even though they are overlapping, peak of one subcarrier is at nulls of the other subcarriers. You can see. Suppose if we take this peak of this carrier, at this peak point, other carriers having nulls here. You can see. Okay, this is the concept of orthogonal frequencies. When we take the integral of the sine x and sine 2x over a period of t, you will get 0. It's nothing but the dot product of two vectors. Okay, so there is no problem. There won't be any overlapping between two subcarriers because they are separating with an integer number: sine x, sine 2x, sine 3x, sine 4x, sine 5x. I take the dot orthogonal side by side carriers are orthogonal to each other. Okay, orthogonal means sin x and sin nx over a period of time. Integral is nothing but the 0. Okay, so this is the main benefit of the bandwidth waveform signal. Originally, it was like this with FDMA because of this orthogonality of the frequencies. All these frequencies comes into nearer. Okay, like this. This much of bandwidth is saved. This is to explain how bandwidth is saved and of the waveform symbol can this one. Anybody is having doubts in any one of this? Hello?
Yes, sir.
Shall I stop or continue? Let's stop at this moment, please.
Sir, one doubt has expressed in chat box, sir.
So where, madam?
Which algorithms are used in 5G?
Which type of algorithm?
Which clustering algorithms are used in 5G? By Saravana Kumar.
Okay, I will answer it later on. Okay.
Okay.
Okay. Any other doubts, please? Let me stop at this moment. I have number of slides I have, but I believe it is the right time to stop it now because continuously speaking for 2.5 hours, 3 hours time is not correct. I have session 3 also for detailed discussion of the channel modeling. I am not doing here now.
Participants, you may unmute yourself and you can express your doubts and clarify your doubts.
Okay, madam. If there are no doubts, let me close it.
Hello, sir. Can you able to hear me?
Please.
Sir, when we talk about this MIMO,
Okay.
do we have a more interference, electromagnetic interference problems, sir?
Yes. Okay.
So, what sort of problems we can expect, sir?
EM by EC problems.
Yes, sir.
Right now, I am not able to answer that question. MIMO EM by EC.
Yes, sir. Thank you, sir.
That right now I may not be able to answer that question. But here
Sir?
we have, pardon?
Sir, I have one doubt, sir.
Please.
Sir, we have different bandwidths like 20 megahertz, 15 megahertz, 30 megahertz. So
Okay.
if we are moving from LTU to 5G, we have different flexibilities of bandwidth, sir.
Yes.
Right. In what way these are advantageous, sir, with
Which one?
respect to
Which
which
one?
parameter?
This bandwidths of OFDM system. Huh?
Yes, sir. Yes, sir.
OFDM varying bandwidths. We say 3 megahertz, 5 megahertz, 15 megahertz,
Yeah.
20
Yeah.
megahertz.
Yeah.
So for different applications they are using, madam. For Wi-Fi under Wi-Fi also they are using 5 megahertz na bandwidth.
Okay.
So
Okay.
depending upon the application, because Wi-Fi may not be able to cover the whole, like cell coverage area is different. Means population density, the number of users to be served is different from one application to other application.
And while using these bandwidths and number of subcarriers need to be same for all the bandwidths, or it should maintain 15 kilohertz of bandwidth.
Same subcarrier bandwidth only we use. And one more thing, as you asked, one more good question.
Yes.
That subcarriers, the more the bandwidth, the more the subcarriers, the more the capacity.
Yes, yes, sir. More number of subscribers can be accessed.
More number of subscribers can be used, and different more the subscribers, then I can go for more different modulation techniques also.
Okay.
Unlike other cellular systems, here I can go for some subcarriers if the channel conditions are good. For some subcarriers whose channel conditions are good, I will always here channel is the most important thing in all cellular communication.
Yes, yes, sir.
The channel condition is good. I may go for 64 QAM or 256 QAM.
Yes.
With higher and higher data rates, I can provide that particular user 1 Gbps speed easily by using 64 QAM.
Right.
Suppose if the user is residing in a multiple buildings area,
yeah, yes,
then my channel conditions are not good actually.
Yes.
If I try to provide the modulation onto the subcarriers, 64 QAM or some QPSK, you won't receive anything. The signal level received at the person who is residing inside the building and underground or something like that, indoor stadium, he may not be able to receive my signal. That time I have to use the BPSK signal.
Okay.
Which provides me the more SNR.
Company norms. I want to know about what is the additional features going to become in 6G network.
6G network, you want to know? Okay.
Yeah, 6G. Yes, 6G.
6G, I'm not having idea about the 6G. 5G itself is not realized.
Yes, sir, relay, but he is now working programming and the protocols, everything he is designing in the 6G, but he is not revealing anything because as per the company norms, he is not revealing. He is working under Samsung only.
Yeah, I understood. Mr. Sarvan Kumar, what I want to tell you, there was no 4G at present. Currently, we are using 4G telephones.
No, yes, sir. LTE only we are using.
Exactly, but there is no 4G.
Yes, sir.
Why there is no 4G is this 4G means as per the 3GPP and 3GPP guidelines, we should achieve, operator should achieve the a minimum speed of 100 Mbps at the peak. So no telephone operator is able to achieve more than 50 Mbps. So it cannot be considered as a 4G, even though they are using the OFDM technology. Everywhere we are using the OFDM, even all modems, underwater communication, everywhere we use the OFDM. But they are not able to achieve the higher speed, the speed requirements of the 4G. So that is why it cannot be considered as a 4G technology completely, because they are not using all the other techniques of 4G, like MIMO communication, they are not using fully. Wavedom they are not using fully. Variable and dynamically varying modulation techniques they are not able to use it fully. So that is why they were using they have named it as long-term evolution, but they have named it as 4G. See 5G nowhere it is implemented with the designated frequencies of the 5G. 5G we are right now they are trying to implement it with lower speed rates than the designated speeds with 10 gigahertz frequency. So once we go for the 28 and 60, 90, then only we can see whatever goals that we have not at all achieved. Only 20 to 10% of the achievement only done. So I exactly do not have any idea what is the need for going for 6G and by bypassing the 4G exactly. I can tell the reason why we should go for the 5G, bypassing 4G, but I cannot tell why 6G without complete realization of the 5G. Hello, Saran Kumar.
Thank you, sir. But I am damn sure, sir, my friend is working under the 6G protocol. He is give white papers also for me, what he is doing also. But he is not revealing the exact solutions, because it is going to be come on 2025, he is saying that one.
Yeah, you're right. I'm not saying.
But I don't know what is the future, because we already have a 4G with the lowest LTE only. Implementing the 4G itself, we needed 2025. 5G, we don't know 2030 or for 2040. But 6G, it is going very fastly. They are doing the work, sir, in Samsung. Huawei and Samsung, they are completely doing about the 6G network.
There are Saran Kumar. There are market strategies are involved. Okay.
Yes, sir, that's okay. But my friend is working on that one. I don't know what is the additional features is going to become. That's why I'm asking you.
Yeah, correct. Additional features. We can talk about the additional features once you have the original features. Original standard 5Gs are not released right now.
Yes, sir. Yes, sir. 4G it should not come in India, sir. Many places 3G only, sir.
Yeah. What is the need for bypassing the 5G and going for 6G?
Okay, sir. Thank you so much, sir. Thank you, sir. Thank you, sir.
Thank you.
Okay.
Sir. Thank you, sir, for your valuable lecture.
Thank you,
Sir,
madam.
we have, you have, sir.
Thank you all, I'm saying, for their patient listening.
Sir, you have covered starting from fundamentals of wireless communication to the new technology, sir. Thank you very much, sir. Thank you for your valuable lecture.
The most difficult part in teaching in online is the most difficult part. Very, very difficult thing.
Yes, yes, sir. Yes, sir.
Thank you, sir.
Thank you.
Thank you,
Thank you,
sir.
sir. Thank you very much.
Thank you very much, sir.
So, dear participants, please join for the third session at 2 o'clock. The session will be followed by our Dr. V.V. Mani Madam from NIT Warangal, Telangana, Hyderabad. So kindly join us at 2 o'clock. Thank you.
Okay, ma'am.
Okay, madam. Yes.